The next speaker is David Miyamoto from Max Planck Institute, and he will talk about Lie groupoids determined by their orbit spaces.
Okay. Thank you for the introduction. And I'd like to say thank you to the organizers for the invitation and for putting together this wonderful event. I'll get into it. We're going to start with a chart, and hopefully everything in this chart is understandable to everyone. So we will have some relation that we'll consider on a manifold. We'll look at its topological quotient space, and then we'll look at its so-called diffeological orbit space. So let's see, what's a simple relation? We can act on R2 by rotation. So the cyclic group Zm acting on R2. Now, if we take this, we know somehow in our heads that this is a cone, right? We take the plane, we fold it. But if we take its topology, we don't see that. Topologically, this is just the plane. So how do we see it? Well, the diffeological structure is going to be a structure we can put on a set, and this structure, whatever it is, will be distinct for each m. So these are distinct for all m. That's a simple relation. Here's another one. We can act on R by the additive subgroup Z plus alpha Z. So here alpha, to keep this interesting, let's make alpha irrational. Otherwise, we'll just have a circle. So Z plus alpha Z acting on R. And at the same time, let's consider two relations at once. Here is something acting on R, and here is a partition of some other manifold. So it will be the torus, where xy is related to x plus t, y plus alpha t. So this is a relation on T2, which we'll view maybe as R2 on Z2. So let's consider both of these relations. If we take the topological quotient, well, maybe this one is the easiest to see that it's coarse. There's only two open sets, the whole thing and nothing. But the diffeology will see some finer information, and we have this result. So T alpha will be isomorphic to T beta in this category, if and only if alpha is related to beta mod GL2Z. So by homographies. And this is from Patrick Iglesias-Zamor. And Donato in 85. And one more relation. Yeah.
I don't understand what alpha congruent is.
Right. So this here just means that alpha is equal to beta A plus B over beta C plus D, and A, B, C, D is a GL2Z. Yeah. No problem. All right. And let's see, one more relation. So A will be GLNZ. Maybe I'm using different notations here for GLN, with no eigenvalues of norm 1. And this will induce an action on the torus by iterating applications of A and then taking the quotient. So something like X will be related to AX on Tn. This is a simple example of an Anosov diffeomorphism of the torus. And the topological quotient here, I have to admit, I'm not going to write some answer. But we can tell apart their diffeological quotients in the following way. So Tn mod A is going to be isomorphic to Tn mod B in this category, if and only if A is conjugate to B or its inverse, perhaps. And this is Cabrera, Pujals, and Del Hoyle in 2019. But here, when I write these names, they were not working in diffeology. They were using a different structure to model these quotients. It's one that we've seen before in this conference. They were using stacks. And whereas a diffeology is something that you place on the set, maybe in the same vein that you put a topology on a set, the stack is maybe something you begin with by taking the action, forming a groupoid, and then modding by some Morita equivalence relation. So the theorem that I'll write next is going to say that I can, in this column, put equally well stacks. And it's the exact same results. So these stacks are isomorphic if and only if this relation. These stacks are isomorphic if and only if this relation. And what we're seeing is that in these cases, the diffeological structure is telling us exactly, well, more or less what the stack is telling us. Okay, so this is my, more or less, yeah, so that's coming. So hopefully this board was understandable. Now I'll write a board where I know at least one thing will not be quite understandable, because I'm just going to put the main result and we'll work through how to interpret it. So this is theorem, me 23. It grew out of work that I did for my thesis with Yael last year. We have a version of this, and then I've sort of changed it, maybe done a bit more. Thank you. So the functor, which does this, is say to Lie groupoid to its orbit space, M mod G, so orbit space. So this is Lie groupoid. And this is now going to be equipped with its natural diffeology, which it will inherit from M. So it's in the category diffeology. Gives an equivalence. And then it's an equivalence of what? So of the categories, there's two equivalences we'll consider. One is of the so-called lift complete Lie groupoids, which are also étale and effective Lie groupoids. And that's going to be on the groupoid side. And on the diffeology side, we'll have so-called quasi-étale spaces. So these are the words that I know that you won't know, especially this one, because I had to come up with it. This one, however, I did not. This was Villatoro, 23. And these appeared, he was integrating the algebroids, and he found that these were the right spaces to form the arrow spaces of these integrations. So these existed, these perhaps I had to call something. And now if it's the categories, I also need to say what the arrows are. And this is the more or less part of what I said before. So the arrows here are isomorphism classes of submersive bibundles. And if most of these words maybe don't make quite sense, submersive, there's some version of submersions in this some category of Lie groupoids, or some bicategory of Lie groupoids. So there's submersion-like arrows. And down here, again, it's also submersion-like arrows, local subductions. Okay. So the categories are equivalent if you restrict the arrows, but if you take all the arrows, they are not equivalent. However, this is part B now. If you add one more condition to here, which we will get to in a second, so it's the exact same stuff, except you also add something called condition Q. And I'll discuss this later. Here, we'll have something called Q manifolds. And I'm also not responsible for this one. This is Bar, in 73. But also, they came again in diffeology from Ahmadi, Ali Reza Ahmadi, and 23 under the name diffeological étale spaces. The point is that they exist. Then we have an equivalence for all arrows here and all arrows here. So these categories are truly equivalent, whatever they consist of. These are truly equivalent. I know this means something else maybe to most of you, Q manifold, some graded thing. In the 70s, there were a lot of these structures on leaf spaces of foliations. Every generalized manifold had some letter, Q manifold, QF manifold, F manifold, etc. And so for historical reasons, I will call them Q manifolds. Okay. Q? I don't know what it stands for, but yeah, I'm going to give the definition now of what these are.
This is very new, isn't it?
Well, this is something that I haven't emphasized in talks before, and I thought now is a good time to emphasize it in talk. These are all in the preprint, which has a similar name to this talk. Okay. So yeah, these ones are truly equivalent. All right, now I put up so many words that are not defined. Oh, but there's a corollary determined by their orbit spaces. Here, it just means this thing about Morita equivalences. So at the very least, we see that Morita equivalences are submersion-like arrows. So Morita equivalence or Williams equivalence correspond to diffeomorphisms. Okay, so there we go. There's the theorem. Now, there's a couple of things we don't know. So the first things, I will go over diffeology perhaps, but very briefly. So in words, I will just tell, or well, I'll say here. So a diffeology on X consists of a collection of plots, which are just functions from open subsets of Cartesian spaces into X. And we consider all n's, n bigger than or equal to 0. So if I had a manifold, I need to tell you what the charts are. If I have a diffeology, I need to tell you what the plots are. At the same time, the plots do not quite function like charts of a space. They're closer to, when Eugene was in his talk, these differential structures telling you what the smooth functions out. Here, I tell you what the smooth functions in are. Okay, so this is what a diffeology consists of, satisfying some axioms. I could say it's a concrete sheaf on the site of open subsets of our n's. If that makes sense to you, that's good. If not, that's fine. And so here's some things we need to know about it. So they pass to quotients. Hence, I can have this column in my chart. And also to subsets and to function spaces. And historically, that was the one emphasized. Suriot introduced diffeology in the 80s to deal with infinite dimensional groups of symmetries. Sorry? Yeah, exactly. Yeah. So we can put the topology, the D topology. You just make all the plots continuous. It's the finest one where all the plots are continuous. And we also have the notion of smooth functions. Well, you're testing smoothness with these plots into the space. So F composed with the plots needs to be smooth. So this would be FP, or P. So now we have a category, so I can talk about arrows. And finally, if M is a manifold, and maybe it could be infinite dimensional manifold, then there's a natural diffeology to put on it. If somehow we already decided what the smooth function should be for some other reason, some manifold structure, then the diffeology, we can equip it, is just saying, okay, well, the plots would be whatever smooth functions are coming from that manifold structure. And that's a full and faithful embedding of category of manifolds in diffeology. And it does work for infinite dimensional manifolds too, perhaps whatever that means. Although the faithfulness becomes subtle. Sorry? Oh, M, yeah. Here X is M. Okay, good. And there's just one diffeology that's important. Well, there's many, but for us, it's the quotient diffeology. So I'll just draw what the plots of the quotient diffeology are quickly. So how can I tell if some P into a quotient set is a plot? How am I inducing my diffeology? Well, I require it to have local lifts through every point. So I need to be able to lift locally. And this looks like a submersion type property for the quotient map. And we know from manifolds that submersions determine the smooth structure on their base. So here, the smooth structure is being determined by pi. Okay, so here's diffeology. So I have 10 minutes or 9 minutes. Is this correct? Okay, thank you. So now let's get some of these words. Because I'll cheat a bit. Because it's an equivalence of categories, if I tell you what lift complete Ital groupoids are, essentially, then I tell you what quasi-Ital is. So I can tell you the left side, with the right side will be the orbit spaces of such things. So for simplicity, I actually will just work with action groupoids. But you can ask me some other time about the general case. So here we have an action groupoid, G acting on M. So the arrows of this groupoid look like that. Pairs take X to G times X. This is just the action groupoid. Now, I'll say one thing about these submersive bibundles, which is tell you what they are, and then I won't say anything more about them. It's not just functors between groupoids, where you sort of invert certain functors to get this bigger bicategory, such that these Morris equivalences become equivalences. So here is, I'll draw a bibundle. You have some P. We're trying to get an arrow between M and N, where G is acting on M and H is acting on N. So two action groupoids. We want something between them. The something is a bibundle, P. So bundle, there's a G action on P and an H action on P, which commute. And this one here is principal. Principal on one side, so we're going from left to right, and we're not necessarily able to go from right to left. If it's principal on both sides, then you can kind of go back and forth. That's called a Morita equivalence. And the submersion part, that's if this arrow here is a submersion. So in general, I'm not assuming anything about this arrow. Well, it's H equivariant, I guess, but that's it. So if it's a submersion, that's a so-called submersion bibundle. It doesn't need to necessarily be surjective in this case. Yeah. All right, so now finally, maybe it's good to get to actually telling you what is here. So lift complete for action groupoids. The lift complete condition is as follows. If I'm ever in this situation where I have a smooth function which descends to the identity on the quotient, or put another way, it lifts the identity, maybe only locally, then I need the following to be true. It's a strong condition. For every point in a W, there needs to exist a G, really an arrow, but here the arrows are basically group elements. So it exists a G such that F, the germ at F, germ at X of F is a germ at G at X. So this is my notation for germ of a function. And it means that the only things that lift the identity are basically the group elements and nothing else. That's why it's lift complete. The only lifts are already here. There's no other lifts. And this Q condition is lift complete, but yet even stronger. And this is kind of phrased diffeologically. So if you have two plots of your manifold pointed, so they take some R to some X, they're taking the same point to a point here. And this is an equalizer, a co-equalizer. Then the germ of P at R is the germ Q at R. So you can kind of think of this as your lift complete, so there's no lifts other than the group elements, and lifts are basically, like, lifts are basically determined by where they send points. But this is even stronger, again, than that. Although, for group actions, maybe it's not quite stronger. Free actions, typically, if it's free plus lift complete, it will be Q. So here, just think of it as some kind of freeness condition on your action. All right. And there's a tau effective. So a tau is just that the dimension of the arrow space is a dimension of M. In this case, for action groupoids, that means that G is zero dimensional. And effective means that no two arrows do the same transformation. So no two group elements have the exact same effect on your manifold. I'll write it down. So effective is that if Gx is G prime x, then G equals G prime. Okay, so I have 4 minutes. All right. So at this point, I hope I've motivated some kind of question. Does diffeology see what the stack sees? In these cases, they do. I mean, I chose these cases because they do. And I've told you a bit about diffeology. We've defined key terms here. And then again, so quasi-étale spaces will look like quotients of étale lift complete, the groupoids. And Q manifolds will look like quotients of Q lift complete groupoids satisfying condition Q. And the arrows are bipedals. OK, so in the last 3 minutes, then, I will just give some examples. All right, so there's key examples here. So if G acts on Rn, where G is a subgroup of the affine group and is countable, then you form lift complete Lie groupoids. So examples means that they are lift complete. That's what it means to be an example. And in this case, I have some literature to talk about. So this is a model quasi-fold. These were introduced by Prato in 2001, and Iglesias Zamor, Patrick, and Elisa Prato in 2020 introduced them into diffeology. Prato was extending the Delzant theorem. So if we briefly remember toric symplectic manifolds, you have a polytope, the momentum polytope. It can be Delzant, rational, and simple. Then you can reconstruct manifolds with that image. If you drop if you drop Delzant, then you can recover symplectic toric orbifolds. This was done by Sue and Eugene. And if you drop rational, you end up with these quasifolds. So that's where these quotients appear in topics maybe relevant to this group, to us. And if you take these groupoids, this is where this project grew out of, then you get a quasifold groupoid. And this was Eyal and I in 23, which has made its way to transformation groups recently. Okay. And another remark about this example, I have 1 minute left, is that with the Lin, who's also here, we showed that certain foliations always have leaf spaces which are quasifolds. These need to be so-called killing Riemannian foliations, which are related to quasifolds in some way, related to Prato's work in some way. So these are examples. And I'll just say the last example. You can also take countable subgroups of isometries of a Riemannian manifold. That's also an example. And these two examples are both examples for the same reason due to some PDEs. And I'll end there.